Here's an example of this in one dimension. Suppose that this is the function that I'm trying to approximate. So this is the true function that I'm trying to predict values for. Except, of course, I don't know what this true function is. If I did know, I wouldn't be predicting it. What I have is I have some observations from this function. So for when x is equal to 1, y is equal to 4, and when x is equal to 3.2, I get a 6, and when x is equal to 5, I get a 3. And these observations, these points, this is my training set. And I don't actually see the function itself. I just see the points. So realize that that's what the algorithm sees. That's the input. So if that's the input, how does the algorithm work? Suppose I want to predict the label, predict the value for x equal to 4. How do I do that? Well, it's pretty simple. I look for the distance. I look for the nearest neighbors in the x space. I'm predicting the y. Y is not an attribute. Right? So I'm just looking at the x values of all the points. The nearest neighbor is this 3.2. So if I were using a one nearest neighbor algorithm, the prediction for 4 would be just the value of 3.2. So it would be 6. So that would be the prediction for x equals 4 based on a one nearest neighbor algorithm. And you look at it, it's not particularly good, right? It's pretty far from where it should be. So what if we took a two nearest neighbor algorithm? Two nearest neighbor, now you're looking for two training points that are closest to 4. So that would be 3.2 and 5. So I'm going to take, for 3.2 I get a 6, for 5 I get a 3, and I'm going to do the average of them. So it's 6 plus 3 divided by 2, you get a 4.5. So that would be the prediction for the two nearest neighbor algorithm. And I could take it further, right? I could do a 3 nearest neighbor algorithm, in which case this point 6 would be drawn into the mix. That's the third closest neighbor, and that would be the prediction for the 3 nearest neighbor algorithm. And these are, of course, closer to the truth than the one nearest neighbor prediction was, but you notice that there is a sweet spot, right? So it's not the case that the more neighbors you take, the more accurate you're going to be. In fact, what happens if you take all the neighbors? You just get the mean, right? So there is a sweet spot in terms of the number of neighbors that will give you a good prediction, a prediction that's as close as possible to the true value. Now, that usually happens for points like 4, but there are points where things like that will not happen. So a good example of that is point 0. So suppose I want to predict the value of y when x equal to 0. Is there a good value of k that would allow the k nearest neighbor to predict that? No. All of the predictions are going to be really, really bad. So if I take 1, then I'm going to predict a 4. If I take 2, then I'm going to predict a 5, and none of them are going to give a reasonable prediction. And one particular reason why this is happening in this case is there is a fundamental difference between the point 4 and the point 0. The point 4 lies in the middle of training examples. The point 0 lies outside of the range of the training examples that you have. And there is a name for this thing. So what you're doing in 4, you're doing regression, but the particular kind of regression is usually known as interpolation. So you're predicting a value for a point which is within the range of your training examples. And for 0, you're doing extrapolation. You're predicting outside of the range for which you have examples. And extrapolation is usually a lot harder. It, of course, depends on the particular function that you're looking at, but usually extrapolation is a lot harder.